Okay, so this is the solution video for paragraph number 4, which oddly enough I don't actually think has a paragraph in it, but that's okay. Still good practice. So it looks like we have a pendulum that's going to be swinging back and forth. So some things that I know about pendulums. I know the period of a pendulum can be found by doing 2 pi square root L over G, and the mass doesn't matter. I know that the horizontal, or rather the displacement, as a function of time is xa cosine 2 pi ft. I know that there's a conversion of energy between gravitational potential energy and kinetic energy. And I know that the forces involved, we're going to have some tension forces, we're going to have some gravity, we might need to deal with centripetal forces or net forces, who knows. So then I'm presented with a graph of horizontal position versus time. Remember, the slope of this graph gives me information about the velocity. Okay, so one end of the string is secured to a ceiling, and the other end is attached to a sphere of 0.2 kilograms. The sphere is raised to an angle of 15 degrees above the sphere's equilibrium position of release from rest so that the pendulum oscillates. Location 1, is shown in the figure. A graph of the pendulum's horizontal position as a function of time is shown. First thing we need to do is, on the dot, represent the sphere at location 2, so when it's hanging straight down. Draw a free body diagram that shows and labels forces exerted on the sphere, and we need to draw the relative lengths. So at location 2, when we're on the bottom, I definitely know that there's a force of gravity and a tension force. Now, what a lot of people mistakenly do is they mistakenly say that these two forces are equal. But they're actually not, because remember, this pendulum is also undergoing some circular motion. And the net force for any object undergoing circular motion must point towards the center of the circle, which means whatever force points towards the center of the circle needs to be larger than any forces pointing out of the circle. So my tension force needs to be a little bit longer than my force of gravity. So I'm going to make tension 4 boxes and force of gravity 3 boxes. Then in part B, I need to calculate the maximum kinetic energy of the sphere as it oscillates. Now normally when I calculate kinetic energy, I do 1/2 mv squared. And while I have the mass, I don't have any information about the velocity. So I want to think about, or actually, wait a second, I do have information about the velocity because I'm given this horizontal position versus time graph where the slope of which is velocity. So I need to find where that maximum kinetic energy is. And remember, the maximum kinetic energy occurs at position 2, which is going to correspond to a horizontal position of 0. So any of these locations, I need to find the velocity at that point. So the velocity is just going to be the slope of the line tangent to the curve at that point. So essentially this line. So my slope, remember, is change in y over change in x. So I have a slope of about, so let's see, 0.2 minus negative 0.2 over a delta x. So this is going to be fun. It looks to be like a little bit greater than 1/2 second. So maybe like, I don't know. Let's see, 1, 2. So it looks like 3, 4, 5. So that would be 2/10 of a second each. So I'm going to say 0.6. That sounds good to me. 0.6 seconds. And these are meters. So that leads me with 0.4 on top divided by 0.6 on the bottom to find the speed. So let's see, 0.4 divided by 0.6 is 0.7 meters a second. So now I'm going to take that and the mass, which is 0.2 kilograms, and come down here, and I'm going to do 1/2 0.2 kilograms times 0.7 meters a second squared. So 1/2 times 0.2 times 0.7 squared gives me a kinetic energy of 0.049 joules. All right. Then the sphere is raised to a new angle above the sphere's equilibrium position that's less than the angle described for A. The sphere is released from rest so that the pendulum oscillates. Explain how the motion of the sphere changes, if at all, based on appropriate evidence. Okay, so let's see. Let's talk about the major things that we might need. We might talk about displacement. We might talk about period. That's pretty much all I can think about. Let's talk about maximum speed. All right, so period of a pendulum is 2 pi square root length over acceleration due to gravity. Okay, the initial displacement is not anywhere in that equation, so the period is going to remain the same. So I'm going to talk about that first. The period of the pendulum will remain the same because initial displacement does not affect the period. Okay. What that initial displacement will affect is the amount of energy in the system, because that initial displacement is going to affect the height of the pendulum. Okay. However, at a smaller angle, there will be less energy in the system. And if there's less energy but with the same mass, this maximum velocity will decrease. So, and V max will be smaller. Okay. So period of the pendulum is going to remain the same, but what is going to change is the amount of energy in the system, and it ends up making it so that the velocity at that position 2 is smaller. All right, so let's go ahead and check the points. So I get 1 point for drawing an upward tension and a downward gravity, and then my other point is for drawing tension that's larger than gravity. Remember, we needed to do that because this pendulum is also moving in a circle, and in order for the net force to point towards the center of the circle, the tension force needs to be larger than the force of gravity. Okay. Then we needed to calculate the maximum kinetic energy. Okay. So it looks like they went about this a little bit differently than I did. Okay. So let me walk you through what they did. They got a different answer than I did, and I'm wondering if mine would also be correct. So what they did is they found the period of oscillation from the graph. So they looked for one complete sine, or that's a cosine wave, or one complete sine wave. Okay, so they got a period of about 2 seconds. So let's just see if that matches up. Okay, so let's see, from here to here, yeah, that's 2 seconds. So we have a period of 2 seconds. All right. So G, they use 10. If you use 9.8, let's see what we would get times 4. These two cancel, so I'm just going to divide by pi squared. So that gives me 0.993 meters. Okay. Then remember, you can find the maximum height or maximum displacement for the height by using this equation here. This would be a good one to add to your reference table. Okay, so if we use that 0.993 that I just got, we end up getting 0.993 minus 0.993 cosine of 15, and we're using 15 because that's the initial angular displacement. And that gets me 0.0338. Okay. And then they use conservation of energy, and they find the maximum potential energy, okay? And use that to calculate the maximum kinetic energy, because we know gravitational potential energy converts to kinetic energy. Okay, so that's what they do here. So they do 0.2 times, excuse me, times 10 times 0.034, so 0.2 times 9.8. Yeah, and we get about 0.06 8 joules. But I feel like you could still get full credit for the way we did it as well, using the slope of the graph to help us find velocity. So I'm a little torn there, but when I go through and grade these, I'll make sure to accept both ways. All right, and then part C, we had to talk about how things would change if we are at a smaller angle. So we get 1 point for stating that the period of oscillation remains the same, and then 1 point for stating that the period of oscillation only depends on gravitational field strength and length. So did I actually say that? Let's see. Oh, initial displacement does not affect the period. So, yeah. And then I actually wrote a little bit more than I needed to, but it's always good to, if you know you're correct, it's always good to include a little bit more, because you never know with these AP graders what they're going to look for. Okay. That is the end for this paragraph number 4, which again wasn't really a paragraph, but still good practice. See you all soon.